At the Augmenting Robots, which is a cluster of the Center for Integrated Emergency Management, and also at the Artificial Intelligence, Biomechatronics and Collaborative Robotics Research Group, we have a dream. We want to enable what we have defined as human-robot teaming, which means that we want humans and robots working together synergistically. Hello, Arish. So we have so far highlighted the concept of human-robot teaming, and within this new research field that we are trying to envision, we have one possible application within emergency management. And in this perspective, Harish is working with snake-like robots.
So our main motive is to make a snake robot where we can use this for search and rescue situations. If you see most of the disaster situations, you need to go into the trapped terrains. So that is very difficult with the normal robots. So that's why we need snake robots to take into the situation and make the snake to move through the smaller terrain and narrow areas. So our main goal is to make the snake robot to solve that problem, to get into the disaster situation. So I'll show you the demo, like what exactly I'm working on. So to run the snake on the multi-terrain environment, so it is very important to look at the control aspect as well. So for that we are looking at different control designs for this. So this one is kind of adaptive controller which adapt to the multi-terrain locomotion. So if the friction changes, then this try to change its control properties so that it can adapt to the terrain.
So our journey of exploring this new concept of human-robot teaming has a key element, which is digital twins. So we are building digital twins, and Evan here is representing our master person on building digital twins. And here we would like to show a demo of one of our first real digital twin that we have made with Slamrensing, a Norwegian company that is working within constructions.
So this is a project I worked at in Twilligent, where we developed digital twins for industrial application. This digital twin is of a water treatment plant, where we connected 3D models with live data to provide an intuitive interface that includes troubleshooting guides, fault detection, checklist of routines, and so on. So it's interactive. When you press on an icon, you navigate to the part in the model, and you can see warnings and go through troubleshooting guides, and it will basically guide you through step by step on how to resolve issues with those plants. We're looking to use the same kind of technology for human-robot teaming within this research group. So this is a very exciting technology that we look to expand the use of in the future.
Our vision of teaming up humans and robots has several applications. And our research is actually overlapping, and it's actually coexisting and collaborating with the Center of Integrated Emergency Management, or CM. Within CM, we have a cluster that is called Augmenting Robots. The idea there is to augment people, so civilians and first responders, with robotics in a potential disaster scene. So we want to enable first responders to possibly save as many lives as possible, and civilians to save themselves as quickly as possible For example, if this building is collapsing, we could use robots, like a drone or a snake robot, to lead the people outside the building as quickly as possible. So in that case, we are teaming up civilians with robots. And another possible scenario is augmenting first responders, for example, fire stoppers, with robots so that they can lead their way to save as many possible lives within the collapsed building. So in the second case, we are teaming up first responders and robots. Within the idea of using better sensors, we are exploring different possibilities, and here we see Hamza wearing an electromyography sensor, which is used to measure the activity of muscles. So this is another possibility that we are exploring to connect humans and robots and interface them with each other. And as you can see here, we have different channels monitoring different activities, and we can visualize this into this nice time plot.
This is an 8-channel IMG sensor, and it is detecting the muscle movement in a real time. When we're talking about the intention predictions or the gesture recognition of the human to interface it with the robot, then with the camera there are other ways for this work, like the wearable sensors. And in the wearable sensors we have a technology that is called electromyography sensors, which basically reads the muscle movements. Also it detects the hand gestures and intentions of a human, which can be translated for a human-robot collaboration. So when we talk about search and rescue operations in a disaster environment, then drones or UAVs are a very important factor for the victim identification, for the disaster assessment, and also to find an optimal way for the other robots, ground vehicles, to give the first aid, to help the first responders in their work.
So by pushing the vision of human-robot teaming, we would like to have robots and humans getting closer and closer to each other, sharing space, but also forces. And in this kind of very close physical interaction, there might be potential collisions between the two actors. So that's why we are building robots that have better actuators. So in this case, we are building, Tuan is building a hybrid, rigid, soft robot, where the idea is that the lower part of this robot is going to have to feature strong, traditional, rigid actuators, while the upper part, which is the part that is going to be very close to humans, is going to be soft, so intrinsically safe. If there is a collision with a person, part of the energy will be absorbed and it will be intrinsically safe, even if everything fails, if sensors or software fail.
So in the project, the idea is to design 2 parts. The first part is the mechanical part that have the spring inside. So the design will have in the lower part there are 3 rigid joints, and in the upper part there are 3 other joints with the spring embedded inside the joint here and here. And the second part is to design an algorithm that can limit the interaction force so that it can be safe when the robot contact with the environment in general or with humans in particular. So the spring will be embedded inside the joint here, and there are 2 more springs that form a universal joint here. So we have a 2 degree of freedom joint with elasticity inside.
One of the most fundamental aspect is the interaction between humans and robots. And here we have a demo that Martin has prepared, where we are connecting a robotic hand, interfacing it with humans.
I'm Martin, a master student at the University of Agder, and I have worked with this hand gesture system and mimicking a hand gestures with this robotic hand. It works as the robotic hand is connected to the computer, running a ROS2 system, and using a webcam we can use a AI trained model to analyze my hand, and it will implement the gesture to the robotic hand.
Velferdsteknologi vil hjelpe oss å komme gjennom den demografiske utviklingen vi har hatt i Norge. Vi får flere og flere eldre og færre yngre. Det vil si at det er færre og færre hendre som skal ta seg av flere og flere. For å kunne klare denne utfordringen så er vi nødt til å industrialisere omsorgen, eller vi er i hvert fall nødt til å automatisere og ta i bruk ny teknologi. Det vi gjør her, det er å se på hvordan kan vi utvikle hjelpemidler for eldre, hvordan kan vi forbedre diagnose, hvordan kan vi forbedre rehabilitering av skader. Vår hovedmisjon her er å øke effektiviteten til velferdsstaten vår.
And to enable this new field of study, this new revolutionary pattern, we need three essential key points. We need better sensors, we need better actuators, and we need better control algorithms. When I say better sensors, I mean that, on the contrary, compared to the traditional robotics approach of having sensors just on board of the robot, we also are considering to have sensors embedded in the environment, sensors on board of the operator or humans, so that we increase the level of awareness. In this way, the robot should not only understand what is happening right now, but it should also be able to infer about the next time window, the future. So the robot in practice should be able to understand my intention. If I want to lift a heavy object from this room to the next room, maybe I'm not able to perform this task alone. Neither the robot can do this by itself. So we have to team up, so that the robot, together with the human, can achieve that task. And in that case, the robot has to interpret my intention to move this heavy object to the next room. The second point I was mentioning is to enable human-robot teaming is to have better actuators, better motors. So this means that it's not enough to have to use the traditionally rigid actuators that we used to have in industrial robots. We need actuators that are intrinsically safe. That's why we are designing actuators that are soft or hybrid, partially rigid and partially soft, so that we can get the benefit of rigid robots with the strong torque, but also safety as a first priority. So part of the energy, if there is a potential collision between the robot and the human, part of the energy of that collision can be passively absorbed. In this way, we can ensure safe human-robot teaming. And finally, the last point we are working on is to design better control algorithms. Better control algorithm means that we want to find a trade-off between traditional control approaches and new machine learning enabled algorithms. So to summarize, we are working towards achieving better sensors, better actuators, and better control algorithms. And in doing this, we envision the development of 4 pillars. in the framework of human-robot teaming. The first pillar is increasing levels of autonomy. So the robot will be more and more autonomous. So we are transitioning from a world where we had remote control robots to a world where robots are fully autonomous. The next pillar is increasing levels of collaborations. So humans and robots collaborating, hands in hands together. The third pillar is increasing levels of ethics, because the more we increase autonomy and collaboration, the more we will have ethical challenges to solve. So who is taking the decision? Is it the robot? Are we delegating all the decisions to the robot, even the most ethically challenging decisions? Like, for example, if we are in a disaster area, the robot has to make a choice. Should I save this baby or that elderly person in the corner? Time is limited, resources are limited. The robot is going to take a decision. So the level of ethics will increase. And finally, the last pillar is levels of security. Before, we used to live in a world where robotics and experts in cybersecurity were not communicating with each other. They were exploring their own research area. Now we live in a world where robotics and security, they must live together. They must benefit from each other. So these four pillars: levels of autonomy, levels of collaboration, levels of ethics, and levels of security. These are the key elements to achieve human-robot teaming.